Hello everyone, this is the Controlling Telescope Hardware with Rust talk. We're going to be talking about telescope hardware and controlling that hardware with Rust from a desktop and interacting with our hardware and how to do that. So, who am I? I'm Ashley, pronouns are she, her. All of the code in this talk is going to be on GitHub at the project name Scopy. It's a project name that I've been using for this code. And on the right here is me in Seattle last winter taking an image of the Elephant's Trunk Nebula. And the result of that session was this image. So on the left, you have a very bright star that is blowing lots of solar radiation and whatnot at the gas cloud on the right. More dense parts of that cloud are more resistant to being pushed, so you get these globs of dust remaining behind. And if you really squint, then those globs of dust sort of look like an elephant's trunk, hence the name Elephant's Trunk Nebula. Cool. So we're going to be talking a little bit about how astronomy and astrophotography works, in particular my setup, so we have some context of some technical words and an understanding of what's going on before we jump into the code. This is a Newtonian telescope, which is what I have. Light comes in on the left, bounces off a parabolic mirror on the right, then in the middle, or on the left here, is a secondary mirror that redirects the light up top. Then, normally, if you were looking through this telescope with your own eyes, you would have a lens here, but instead we have a image sensor that sits directly on the focal point and collects the data directly, and then we can pull the data off this camera. What that actually looks like in real life is like this. So, light goes in on the left, the mirror is on the right, then buried in the middle here is that second mirror, which redirects the light up top to that camera. Below that is the mount system. So we have two motorized mounts. The top one is called the declination axis, then below that is the right ascension axis. And these two motors combined let us look anywhere in the sky. So what actually are right ascension declination? So the sky needs a coordinate system to be able to uniquely identify any point in the sky. We start off with using the Earth's latitude and longitude as a base. Latitude is easy. We just say that anything over the North Pole, directly over the North Pole, is 90 degrees north. Anything over the equator is 0 degrees. Anything over the South Pole is negative 90 degrees. But the equivalent of longitude is a little bit more complicated since the Earth obviously spins and we can't have our coordinate system spinning throughout the sky. So instead, the Earth uses the 0 degrees longitude is defined as being at Greenwich in the UK. Instead, we define 0 degrees of right ascension, as it's called, as being the direction of the sun at the spring equinox. It's kind of a weird definition, but that's what it is. So cool. Now we're able to uniquely identify any point in the sky and have that coordinate system. Importantly, right ascension and declination are aligned with the Earth's rotation axis. So our own motors need to be aligned with that Earth's rotation axis, which means that we need to tilt our motors equivalent to the latitude that we're currently at. So Seattle is 47 degrees north, and so I've configured my telescope here to be used at Seattle to tilt those axes to be 47 degrees. Cool. So now we're able to point our telescope anywhere in the sky and image whatever we want to. Now let's actually start getting into code. We're going to look into the motors first to see how we want to control those motors. So we do a Google search, figure out the hardware that we have, and we dig up the specification manual that our hardware provider provided. So it's a serial communication protocol. That means it's a tube that you send bytes down and you get bytes back, and it's all serial, and it's very, very simple, and it's pretty great. So in this document are things like 9600 bits a second, no parity, etc. There's various serial communication parameters. If we scroll down in this document, we have various commands that we can send to the motors. So go-to is the term in astronomy to say, hey, telescope, point to this point in the sky. And the way we do this is to send down the serial pipe the letter R, and then a right ascension encoded in hexadecimal, followed by a comma, and then the declination encoded in hexadecimal. Then, in response, the hand controller sends back a hash symbol to say, hey, everything's okay, things succeeded. If we scroll down some more, retrieving data from the mount is a very similar system. We send the letter E, and we get back a right ascension declination in hexadecimal again that says where the telescope is currently pointing in the sky. So that's really useful if things are drifting or whatever. Cool. So we have a serial API, and we want to write this in Rust. And so we look online, and we find the serial port crate, which is a fantastic crate. It's super fun to use. Lets us use serial ports from Rust. So what that looks like is if we want to open our connection to the mount, we give it a path, and we get back our serial port. Then we're allowed to do some configurations, for example, set that bit rate, set the parity, and here we're setting the timeout. So if the serial port doesn't respond for 3 seconds, then we kill the connection. Cool. How do we actually send bytes down this serial port? It's pretty simple. There's this write all method, and we just dump the bytes in this buffer down the pipe. Cool. Reading is a little more complicated. So the trouble is that if we want to read something, we can't just read up until we get a hash, because the data that we're getting might accidentally include a hash symbol, or rather the ASCII value of a hash, in the data that we're receiving. And that's no good. And so instead, we need to get the length of the data that we expect to receive up front. And the way we do that is that we pass in a buffer, and then we use that buffer's length as the amount of data that we're expecting to read. So first, we read the buffer here, so that reads n number of bytes. Then after that, we read the hash that is at the end of every single command. The mount always responds with a hash after doing whatever to make sure that everything's okay. Cool. So connecting those all together, we go back to our PDF document, and we go look up the goto command. So that is sending an R followed by the right ascension declination in hexadecimal, and here we're doing that. So we format a string with the letter R followed by the right ascension with comma and declination. So then we write that, send that to the mount, and then we read back that single hash. So remember, a read method then would read 0 bytes and then read that hash for us. So cool. Getting data from the mount is a very similar system. We send an E, and then the buffer size that we expect is 17 bytes. So that's the 8 bytes of the hexadecimal followed by the comma followed by the 8 bytes of the right ascension declination. Cool. Then the rest of this method is just parsing to grab those 2 hexadecimal numbers out of that blob of bytes. Awesome. So now we're able to point the telescope wherever we want it to do. That's awesome. So the next step is to look at the camera. And so again, we look up our camera's manufacturer, look up some specification PDFs, and we stumble upon this PDF, and we start reading through it. And turns out the way that we interact with this camera is a C API. So the vendor of this camera provides this PDF, as well as a C library that we link to with our Rust program. This function opens up the camera, so initializes the USB ports and everything. And then it returns a handle. And what that handle is we then later give this handle back to the API and says, oh, you meant that camera that you previously opened up. So we're able to interact with a single camera based on this handle. Then how we actually get data off of this camera is this function. So it gives us the width, height, bit depth, etc. And then the final parameter is the actual bytes data that we want to get. And so the C API fills in those bytes, and then we have our image. So fantastic. Now we want to write this in Rust. Thankfully, the vendors also provide a C header. And so what we could do is use something like bindgen to convert the C header into Rust. But instead, I've opted to just hand write all these functions because there's only a dozen or so of them, and it was easier to hand write these functions. So for example, you can see that open function that we mentioned earlier. At the top here, we're linking the library that was provided to us, and so that pulls in that code that was provided. So how do we actually use this? So C obviously expects null terminated strings, so we use the C string type to be able to pass in the string to this function, and then we get back our handle. And so then we do some error checking of if that handle is null, and then we have our camera open. So that's great. So now we want to get some data off of that camera, and so we get the width, height, etc. And then we have a buffer for that C API to be able to fill in that data. Something that I found really useful when working with C libraries is I have this check function, because C libraries usually return integers as error codes. And so I have this check function that takes that integer, compares it against error code, see if it's a success or not, and then returns a Rust result. And that allows us to use that question mark operator, and that's really, really nice and ergonomic to be able to interact with these C libraries. Cool. So now we're able to point the telescope wherever we want to. We're able to get image data off of our camera, and that means we all have all that we need to create beautiful images. So this is an image that I took of the Eagle Nebula, M16. At the center, you can see three little newts. Those are the pillars of creation, the very famous Hubble image, and I was really, really excited to say that, like, I actually captured this with my own amateur telescope, and I, like, saw a thing that Hubble saw. It was, like, super exciting for me. So, yay! So cool. The trouble is that just interacting with the hardware isn't enough. We also have to slap a UI on top of this. So this is a pretty garbage UI, I just slapped it together. But whatever, it has all the data that I need. Unfortunately, this isn't actually a live data. This is just a simulation that I was running with my program. And that's because at midnight, Stockholm looks like this, because the sun is so, like, doesn't get below the horizon at all. So I can't actually do any astronomy right now to get any live data screenshots. But whatever. So the fact that we're putting a UI on top of these hardware functions is kind of problematic, because, for example, downloading the data off of the camera can take a couple seconds, and we don't want to lock up our UI thread for a couple seconds, because that would be really bad user experience, even if it's just me using the program. So we want to have a thread dedicated to doing the camera work or doing the mount interaction work, and then we have our UI thread. And so I want to share some experience that I had working with hardware and what patterns worked really well when working with, like, blocking hardware and stuff like that. So this is a pattern that I really like. So we have our dedicated mount thread here that's just spinning in a loop. And then we have a MPSC channel that instead of sending data over, we send lambdas or delegates. And then we call that delegate with our local mount. And so that means that this mount can only be accessed by this thread, but the fact that we're sending over lambdas means that we can write really nice shim layers like this, that if we want to slew the, or go to the mount to wherever we want to, we just need to write the shim. Then the UI thread can call this method. It just sends this lambda over the MPSC channel, which doesn't block at all, and returns immediately, freeing up the UI thread to do whatever it wants. Then, when the mount thread can get around to it, then it actually does that slew operation, calls this lambda with the mount that is a thread local. And Rust guarantees that this mount will never escape that thread, and it's really, really nice to be able to have those guarantees in this Rust world. Unfortunately, the camera is a little bit more complicated, and I do have an enum instead of sending over lambdas. And this is because the camera is a little bit more complicated. So here we're setting a control, and control in this sense means something like the camera's gain or the exposure or stuff like that. And it turns out that the camera hardware really doesn't like it when you set the gain in the middle of an exposure, like things crash and stuff. And I just figured this out by using the camera, being in the field, doing some testing. And I figured out that you want to cancel the camera before setting any control. So cancel the current exposure. And so now we have this method. We have to make it a little more complicated. And so now we don't use a lambda anymore. We use an enum. So cool. So now we have all this flexibility to do whatever we want. So that was some threading talk, and now I wanted to talk about some of Rust's performance, because it's really important. So if you see in this image, you can barely see the elephant's trunk nebula that I was imaging here. It's a little faint, but hopefully you can see that. But this image isn't actually what's coming off the camera. What's coming off the camera looks like this. No idea if you can actually see what's going on in this image, but it's basically a black screen with a few tiny bright white dots. And the reason for this is the camera has a 16-bit depth. 12 bits actually, but it returns it in the data of 16 bits. So that means it has a very high dynamic range. And if we want to remap that to 8 bits of what our displays actually display, then we're only going to see the very brightest things, which in this case are tiny little dots of stars that are showing up, and we can't see the nebula at all. So that means we have no idea if the nebula is in frame or not. We have no idea how good of quality it is. So what we want to do is, when we're previewing this image in the app, we save all of the raw data itself, but when we're previewing, we want to remap this data to be able to see all the interesting parts of the image and not just have a black screen with a few white dots. So we do that by computing some statistics about the image first. And so here we compute the mean and standard deviation of the image. These look like really simple functions. You just loop through the data, add them all up, and then computing standard deviation is really simple. The trouble is that these images are not small. They're 32 megabytes big. And when I implemented this in C#, it took like a couple seconds to churn through all this data. And that's a problem when you're doing things like planetary astronomy, because in planetary, your frame rate is like 10 millisecond exposure, and you want to collect as many exposures as you can. So you want to have these previews come in immediately. You want to process as quickly as you can. And so Rust absolutely blazes through these functions, and it's really a joy to be able to have these previews just snap in as soon as they're available. So cool. So what that processing actually is doing is saying, okay, so we're assuming that the brightness distribution of our image is Gaussian, which it isn't, but whatever, close enough. And so we want to say, like, okay, let's make -1 sigma on this image to be black and +1 sigma to be white, and clip everything outside of it and just see the interesting data that's in the middle of this bell curve. But we also want to be able to shift it a little bit, because maybe the interesting data is on like slightly high side of the bell curve or whatever. So we have these two parameters of our sigma level of how big we want our gap to be, and then an offset of saying like, hey, we want the mean to be 20% bright instead of 50% bright or something like that. So we have this hunk of math because I want to have these shifts to be a straight remap that's a linear equation that's just y equals mx plus b, that's really fast to do. So on the top, we convert our sigma and our mean offset to be a mx plus b equation, so we have a scale and an offset. Then at the bottom, we just do a multiply and an add, which is really fast. So that's really cool. So then, when we want to adjust our, for example, sigma or mean location parameters to adjust our view, we don't actually have to modify the image at all. It's still in GPU memory, and we just adjust this uniform to be able to display it however we like. So that means we have real-time adjustments of saying like, oh, I want to see the bright parts of this image, or I want to see all the dark parts of this image. And it's super snappy and great. And the reason that we don't have to modify it is apparently OpenGL supports 16-bit grayscale textures, which is awesome, so we can just upload the raw data to the GPU and have that all work. So that's super fantastic. So now you have a great application that can preview all of our astronomy images and save them all, and image whatever we would like to in the sky. Great. So yeah, that's my presentation. All of the code that I talked about is all on Scopy on GitHub. There's my Twitter. My email is just wildcard@capuria.com, whatever creative stuff you want to put in there. And then if you want to see more space pics that I've taken, capuria.com has all of my stuff. Thank you very much. All these links will be in Discord or YouTube, hopefully, wherever you're seeing this. So, yeah, thank you.